Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about reaction mechanisms, and it's actually a three-part series. This first video is talking about how reaction mechanisms work in general, and then the next two videos will be practice problems using the concepts that we learned in this first video. So let's start off with what is a reaction mechanism. A reaction mechanism is a series of elementary steps, okay, kind of like what I have listed right here, that describe the collisions that occur in the chemical reaction, okay? Now, if you're new to chemistry, if this is your first year studying chemistry, you might think that two A molecules are going to collide with two B molecules to form C and D, and that's really not the case, okay? You really don't know what's actually colliding. And in this topic of kinetics, that's what we're talking about, are collisions. So you can kind of think of this arrow right here as kind of like this mysterious black box. We know that the input is going to be 2A and 2B, and we know the output is going to be C and D, but what actually collides is kind of a mystery. You really don't know it just by looking at the balanced chemical equation. So what reaction mechanisms are is a description of what's actually happening inside the black box, okay? And a lot of times you're given these proposals and you're trying to decide if they are valid or not, okay? And there's two things that you need to check to see if a reaction mechanism is valid or not. It has to pass two tests. It has to pass the stoichiometry test, and then it has to pass the kinetics/rate law test, okay? So let's go ahead and get into the first part, which is the stoichiometry test. And to pass the stoichiometry test, all you have to do is add your chemical reactions together, okay? So I'm going to add these three elementary steps, okay, to see if they actually, add up to 2A plus 2B yields C and D. So if you remember, you're going to put all the reactants on the left-hand side. So I got A, X, B, Y, B. So here we go. A, X, B, Y, B. And then for the product side, it's going to go on the other side. X, C, Y, D. X, C, Y, D. And then you cancel out things that are on the same, if something's on the reactant side and the product side, they're going to cancel out. And what I see is I see that X is on both sides, so I cancel it out. I see that Y is on both sides, so I cancel out. Here are my two A's. Here are my two B's. And that's going to produce C and D. This does match the overall chemical reaction. So based on stoichiometry, this checks out, okay? It passed the stoichiometry test, okay? Now let's see if it passed the kinetics/rate law test, okay? In order to do this, the reaction mechanism is going to have one step that's slower than all the others, and we call that in chemistry the rate determining step, okay? And the rate determining step determines the kinetics for the overall chemical reaction. And I have a little demonstration here to kind of show you all this. I have three sized funnels, okay? And they're labeled as small, medium, and large, okay? As you can see, the small one, the hole at the bottom, can fit inside the medium one, okay? So the small hole is smaller than the medium hole, okay? Even though the funnel is a different size. And the same thing for the medium and the large. The medium hole can fit inside the large hole, okay? And it doesn't matter the order in which I put these in. One of these steps is going to determine the overall reaction rate. Okay, so I got large, small, medium here, okay? And here are my reactants, and then when they get to the bottom, that will be the products. And let's see what kind of happens here. I'm just going to pour it in here. And as you can see, it travels quickly through the large. It's already past the large. And what's holding this reaction from going from reactants all the way to products is this second step, okay? Because this is the small funnel. And therefore, the rate of the overall reaction is really just dependent on the slowest of the three steps in our reaction mechanism. So whichever one of these steps is the slowest will determine the rate for the overall chemical reaction. And once again, it doesn't even matter the order that I put these in. I can rearrange them into a different order, okay? The thing that's going to control the rate of this chemical reaction is going to be the speed in which it gets through the small hole. Because as soon as it gets through here, it's getting through the other two, okay? So it's not the medium hole or the large hole. It's going to be the small hole or the bottleneck that determines the rate of the overall chemical reaction, okay? So what we need in our reaction mechanisms is that we need to identify which one is the slow step or the rate determining step. And for our first problem, we're going to pretend that the first step is slow. So we're going to call this the slow step. And if that's slow, by default, we call the other two fast. So this is going to be the first of two problems that we're going to do in this problem, okay? Well, slow, step, fast are the easiest problems to do, okay? Because if this is the slow step, okay, all we have to do is compare the rate law of this particular equation to the overall rate law, okay? Now, this rate right here is simply rate is equal to K times A, or simply A squared. Now, does that fit the rate law for the overall chemical reaction? We have to check. Now, remember, to get rate law for an overall reaction, you got to use experimental data, okay? That's not true for these elementary steps that make up the reaction mechanism, okay? So it's simply just the reactants, okay, for elementary steps. But for overall chemical reactions, you're not allowed to say, hey, oh, it's rate order of 2 because that's a 2, or the rate order of 2 because of the 2. You're not allowed to do that. You actually have to look at experimental data, okay? And this is kind of like the beginning of kinetics. So if you don't know how to do this, you can go back a few videos and find how to figure out the rate law for an overall chemical reaction. But let's go ahead and do this work. Let's figure out what the observed rate law is based on my experiment, okay? So it's going to be equal to K times A to the X, B to the Y, and what we're trying to determine is what is the X and Y using this data, okay? So rate laws will always be the reactants, okay? But to figure out the exponents, you need to figure out or use experimental data. So let's go ahead and figure out kind of like the X here, okay? So to figure out X, we're going to compare experiments 1 and 2. B is staying constant, A is doubling. And when A doubles, the rate quadruples, okay? So that tells us that this has to be a rate order of 2. And then we're going to do the same thing for B, but we're going to compare experiments 1 and 3 because that's where A is constant, B is doubling, and the rate is doubling. So that means rate order of 1, okay? So this is kind of like what we call the observed rate law. And remember, you always get the observed rate law from experimental data. Now, if we look at our problem, and if we say that the slow step is first, okay, then this is the rate law, okay? And this rate law does not match this rate law. It's missing the B, okay, B to the first power. So we would say that this reaction mechanism, when it's slow, fast, fast, is invalid because it did not pass the kinetics test, okay? So this rate law does not match this rate law, so it is an invalid reaction mechanism, okay? And the problem's done. So when the first step is slow, they're really, really easy problems. All you do is write the rate law for the elementary step and compare it to your observed rate law that you get from data, okay? And if they don't match, okay, it's invalid. If they happen to match, then you'd say it's valid, okay? Now, slow step second is going to be the next problem. So we're going to do a what if, okay? What if we say that the second step is going to be the slow step? Remember, in chemistry, the vocabulary word for this is rate determining step, okay? So if this is slow, then by default, the other two are going to be fast. And if this is the case, then the rate here is simply equal to K times the reactants, X and B. Now, at first glance, you might say, oh, this rate law doesn't match this one, and it's invalid as well. But you got to be careful here. We got X in the rate law, okay? And if you look up here, X never shows up in the overall balanced chemical equation, okay? And that's because X is called an intermediate. And you're not allowed to have intermediates in your rate law. So we have to do a little bit more work. And that's why slow step second problems are a little bit more challenging than slow step first problems. Slow step first problems really ridiculously easy. You just compare the rate laws, see if they match, okay? But slow step second requires a little bit more work because you got this intermediate. Now, what exactly is an intermediate? An intermediate is a chemical that's produced but then consumed, and it never shows up in the overall reaction. So there's no X up here. But in this reaction mechanism, it's actually made. But in the second step, it's consumed, okay? And that's why they cancel out. Y is an intermediate as well. Y is produced in step 2, but consumed in step 3, and it never shows up in the overall balanced chemical equation as well. So X and Y are intermediates. And for slow step being your rate determining step, X is showing up in your rate law, and you can't have intermediates in your rate law. So there's something that we have to do, okay? We have to actually pretend that this first reaction is in equilibrium. And I'm going to come back and show this demonstration one more time with the slow step second to try to explain what's going on. Okay, so what's going on is that as this chemical reaction is taking place, okay, if I was to pause it right here, in this small funnel, there's a ton of sand, okay? And that sand is not going to want to stay right here. This is the X, basically. This is the intermediate. And intermediates are kind of unstable. So what happens is the sand comes back up here, and that this first reaction is in equilibrium, which means that the forward reaction is just as fast as the reverse reaction, okay? So if we talk about this first reaction being in equilibrium, this is what it's going to look like, okay? The forward reaction, okay, forward reaction is going to be rate is equal to K times A, which is A squared. And the reverse reaction is going to be rate is equal to K times X. Okay, because X is the reactant in the reverse direction, okay? And that these rates are equal to each other. Well, if they're equal to each other, then K times A squared is going to be equal to K times X. These K's are going to cancel out, and X is equal to A squared. So X is equal to A squared, okay? By doing this work of saying that this first reaction is in equilibrium, okay? If we substitute X is equal to A squared, this is going to become rate is equal to X, which is equal to A squared, times the B. And we see that this does match the observed rate law, and then we would say that this reaction mechanism is valid. So once again, when you have slow step being second, you're probably going to have an intermediate, okay? You have to do the first step in equilibrium and solve for what that intermediate is equal to, sub it into the rate law, okay? And then you check to see if it's valid or not. And if it is, we say that this is a valid chemical reaction mechanism, okay? If you found this content helpful, please give it a like and subscribe. And when you leave that comment, it really pushes this information to other students that are interested in learning chemistry.